In this tutorial, you will learn how to build a full-stack decentralized app from scratch. We are going to build an app where users can upload and vote for images. For the storage of the images, we are going to use IPFS, a decentralized way of storing information by its content. For the frontend part, we will use React with ethers.js, and the smart contract, which needs to be run on Ethereum, will be written in Solidity. At the end of this tutorial, you will not be a blockchain expert, but you will have a good understanding of how things will fit together. Let's start by checking out the starter template. Navigate to the contracts folder and rename the example contract to the vote manager. This contract will be responsible for creating, voting and fetching the candidates. A candidate is simply a user that has uploaded an image. First, we define a candidate. Therefore, we use the struct keyword in Solidity. A struct is like a class, but without any implementation logic. The struct holds all the properties that the candidate has. For example, the name, the IPFS image hash, and of course, the address of the candidate. First, we will take care of creating and storing the candidates. Create a function called register candidate that takes two parameters, the name and the image of a candidate. In Solidity, the visibility of a function is defined at the end. This function should only be called from our front end, meaning outside the contract. Therefore, we will make it external. Because the function is external, we can use the callData storage type for our parameters. CallData is a non-modifiable, non-persistent area where function arguments are stored and behaves mostly like memory. For handling the IDs of our candidates, we make use of the counters library from OpenZeppelin. If you are using the starter template, it's already imported. Create a state variable from type counters.counter with the name candidate IDs. This variable will hold the current ID of a candidate. So the ID is basically a simple number. We increase the value by 1 by calling the increment function. Afterwards, we get the current value with the function current. Whoever calls this function wants to be registered as a candidate. Therefore, we take message.sender and parse it to an address. Now we can create a new candidate. Therefore, type in candidate, memory, new candidate equals candidate, and then pass in all the necessary information that we need. In Solidity, if we want to create a new object, we need to specify the storage type. In this case, it's type memory. Memory lives as long as the function is called. So this object will be erased from memory when the function call is completed. But this is completely fine, because we will store this object in a mapping. So let's create a mapping. Therefore, type in mapping, brackets open. Now we need the key, followed by the value, private candidates. Okay, now let's push this new candidate object into the mapping. Therefore, we type in candidates, brackets, and there the key, in this case the address of the candidate, equals new candidate. Simple as that. Finally, we will emit an event that will act like a response, and we will do this by typing emit. And now we need to define the event. Therefore, type in event and then candidate created, and then emit the candidate created event. Now we will write the vote function, and I'm gonna tell you this is gonna be very easy because of the way how we structured our mapping. The vote function will only take one parameter as an input, and this is the address of the candidate. It's also from type external, therefore we also can use callData again. In our candidates mapping, we will look this key up, get the object and increase the property total value by 1. Finally, I like to return an event again, because it shows that this operation was successful.
So easy!
With that being said, thank you Uncle Rogers. Now let's move on to our last function to retrieve all candidates. The fetch candidates function is responsible for returning our candidates mapping. This function is an external view function. View functions ensure that they will not modify the state, what is exactly what we want, since this function should only read information. In Solidity, we cannot return mappings, therefore we will return our candidate array. We define the return type by typing in returns, round brackets, array of a candidate. And don't forget the storage type, in this case memory. We create a temporary array that will hold our candidates. This array is a dynamic array because we used a new keyword. The difference to a static array is that the size of a dynamic array can grow during runtime. After that, we loop through our candidates mapping to get the candidates. But wait, how we can assess the mapping without knowing the keys? We need a helper mapping to overcome this problem. The helper mapping will use the candidate's ID as a key and the value will be the address. Create a mapping called accounts with viewant as a key and the address as a value. Make sure to add the assignment and the register candidate function. Now we can use the helper mapping to iterate over the candidates mapping. Now we have the candidates assessed through the loop and pushed them into the temporary array that we will return. This approach of retrieving data from the blockchain is of course not best practice. A better way would be using a solution like the graph. The graph is a decentralized protocol for indexing and querying data from the blockchain. We can query the data with the help of GraphQL. We finished the hardest part, writing the smart contract. Take a short break and we will move on with the deployment of the smart contract. First, we need to compile our smart contract. Go to the scripts folder and make sure that the Vote Manager contract is correctly set up. If you are using the starter template, you can write npm run compile to trigger the compilation. Otherwise, you can do it normally with Hardhat, npx hardhat compile. After compilation, we have the bytecode and the API of the contract. Bytecode is used to efficiently store opcodes, and opcodes are the instructions that are executed by the AVM, the Ethereum virtual machine. API stands for Application Binary Interface. It is a JSON file that describes our smart contract, meaning which functions can be called with the corresponding parameters. Now we set up a local Ethereum blockchain in order to test and run our smart contract. We set up the testnet by typing in npm run testnet or the Hardhat way with npx hardhat node. We see an output like this. Copy one of these private keys. We use this private key to register our account for the local testnet in MetaMask. Open MetaMask, choose import account and paste in here the private key. Finally, we deploy the contract with npm run deploy or npx hardhat run scripts and then the name of the deploy script. The deployment is successful if you see an output like this. This is the public address where we can reach the smart contract. Copy this address because we will need it later on. Okay, that was the deployment part. Now we will move on to the last one, the front end. Take a short break and I see you there. Glad that you are still with me. We are almost finished. Go to the frontend folder and open the app.tsx. Create these state variables that holds the information about the candidate's name and image. Also the state variable for all the candidates that we will use to iterate over and show each one of them as a card. Also create a variable that holds the contract's address that we have copied earlier. Create a state variable called contract. This variable is an abstraction of our deployed contract and we will use this to call the contract. In the use effect, we set the contract with a helper function called getContract. You find this function under the utils folder. This function uses ethers.js. Ethers.js is a library that provides us all the functionality we need to interact with the Ethereum blockchain. We start by creating a provider. A provider is an abstraction of a connection to the Ethereum network that provides an interface to the standard Ethereum node functionality. We pass in the window.ethereum as a parameter. But what is the window.ethereum? MetaMask injects a global API into websites that can be reached by window.ethereum. This API allows websites to request users' Ethereum accounts, read data from blockchains the user is connected to, and suggest that the user sign messages and transactions. Ethers.js is wrapping this API with its Web3 provider. From the provider, we can get the signer. The signer is an abstraction of an Ethereum account, which can be used to sign messages and transactions. And here's how we can create the contract abstraction by passing in the address of the contract, the API that we can easily import from the backend folder, and the signer object. Lastly, we return the contract object that will be used in the app TSX. I like this approach of creating the contract because we can easily access the contract from anywhere in the application. Move back to the app TSX file. We now create the inputs for the candidate's name and image. Wire it up with the state variables. Also create a button that will trigger the register candidate function. In this function, we first extract the name of the form data and then calling an async function, the IPFS upload handler. The IPFS upload handler receives the selected image and is calling the Pinata API that will return the IPFS hash of that image. Let me quickly show you how you can use it. Open your browser and navigate to the pinata.cloud. Register an account and log in. Click on the upper right profile picture and select API keys. Create a new key and select the pinning options. Give it a name and press Create Keys. Copy the keys and paste it in the environment file. Now create a new file called IPFS service. Paste in the whole stuff. You can check it out on the YouTube repo I will provide in the description. What it basically does is it sends a post request to the Pinata API with our selected image as a payload and then return the IPFS hash of that image. We will concatenate this with the gateway URL. This whole URL can now be used to show the image. Moving back to the register logic, we now have the name and the image of the candidate, and we will finally call our contract with contract.registerCandidate with the two parameters. After calling the contract, we now need some kind of response. And as I said earlier, this is achieved with events in Solidity, and we can subscribe to these events on the front end. Set up a use effect with a dependency to the contract variable, and make sure that the contract exists, and then subscribe to the candidate created event. With the on function provided by the contract class, we can do this easily. The first parameter of the function is the event name, and the second is the event handler. So the event name is candidate created, and our event handler is just an anonymous function that will call the function get all candidates in order to get the new created candidate. Okay, so let's create the get all candidates function. So we call our contract again, and there we call out the fetch candidates function. We create a temporary array because we iterate over the result from the fetch candidates and push all the candidates into this temporary array with all the properties of a candidate. And then we assign the temporary array to our state variable, the candidates array. Okay, it's time to show our candidates on the UI. Therefore, iterate over the state variable candidates and show each of them in a card or whatever you prefer. Okay, let's start the front end by typing in npm run dev, navigate to localhost port 3000 and register here in candidate by simply put in our name and select an image and then press the register candidate button. And here's an error that I wanted to show you, and what I do is just to MetaMask and then go to settings and go to advanced and then reset account. I don't know why this is happening, but the error will after that go away. Okay, now I press the button again and I confirm this transaction. And here we have our image, our candidate with the image, currently with no votes. And now what's left is to implement the logic for the vote function. Well, let's go. We head over. We are using the onClick attribute, and then here we call the vote function and pass in the address of the candidate. Scroll up to the function section, and then here we create the vote function. First I create an early out and check if the address is valid, and now we can call the contract by simply put in contract.vote and pass in the address of the candidate. And now what we now have to do is to move to the use effect and also listen to the voted event to fetch the new candidates with the updated votes. Finally, move to the UI again for one last time, click the button, sign the transaction, and here it is, an updated vote. Nice! Wow, we covered a lot of topics in this tutorial. We started by writing our smart contract with Solidity, supported by Hardhat, deployed it to our local testnet, and finally connected it with ethers.js from the frontend part. Also check out the written version of this tutorial on dev.to. Don't forget to leave a like for the YouTube algorithm. My name is Johannes, and if you have any further questions to this, let's connect on Twitter or LinkedIn. What topic should I cover next? A video about IPFS or a hands-on about the graph? Write it in the comments. Thank you.